let's get huddled up. Today's practice, we're going to talk about soil resistivity, and we're going to talk about the 4-pin Wenner method. Yes, that's how it's sounded out. It's W-E-N-N-E-R, but it's Wenner, to help obtain soil resistance measurements, and then we're going to calculate resistivity together. This is very important to us corrosion nerds, specifically us CP guys and AC mitigation guys, because we need that information to properly design an effective cathodic protection system. In other words, we need to understand a little bit about the environment that our pipe sits in, or our structure that we're trying to protect, and then where our anodes sit. That soil impacts corrosion rates, it impacts how long anodes last, all kinds of things. Also, in the AC interference world, it impacts some of the same things. It's very similar in that world as well. So we need to know something about the HVAC towers, we need to know something about our pipes, and we need to know something about the environment that it lives in. And again, all that impacts so much. So it can become a very important piece of data that we can assume, but it's much better if we can go out in the field and take some measurements and calculate resistivity, get that data, get it in our database, and make good decisions with it. So moving forward, just to give you an idea, again, you're seeing that word resistivity. Resistance and resistivity are certainly associated with each other, but it doesn't mean the same thing. So we're going to go measure resistance of the soil or earth, and then we're going to calculate resistivity. Resistance is measured in ohms. Resistivity is calculated into ohm centimeters. So we're going to put it into ohm centimeters or ohm meters, but in this case today we're going to go to ohm centimeters, and that's kind of the standard in our world of how we determine when something is low resistivity or high resistivity. This is just my opinion. Anything less than 5,000 ohm centimeter I would consider pretty low resistivity soil. Anything higher than that I would consider pretty high. Again, you could ask 10 to 20 different corrosion nerds and they may tell you something a little different, but in my opinion, anything below 5,000 ohm centimeter is going to be pretty low. Anything above is going to be considered mid to now you're creeping up on the high end. Just to give you an idea, and there's some visual aid there to help you out. The meters we're going to use, just like any tool, there's all kinds of brands, there's all kinds of pros and cons to these different meters. These are three that I chose to show you. There's certainly more out there. The one on the left is made by a company called Tinker & Razor. It's a pretty effective tool. It's their soil resistance meter. They may even call it the soil resistivity meter. You can look it up on their website. It's going to work the same as the other two you see on the screen. Very similar features and an overall really good tool. The other one you see here that's orange in the middle, that's the MC Miller 400A, I believe is that model number. Again, been around for a long time. It's a soil resistance meter, does a really good job. And then the one on the right is probably a lesser known meter in the corrosion control world. It's made by Megger. You can look it up. This is a very good tool. This particular tool, of course, it's going to cost you a little bit more, but this particular tool is very good for measuring soil resistivities very, very deep. You may see folks in the grounding world use a meter like that. And there's some other name brands out there. These are just the three that I'm most familiar with. And so I just wanted to kind of give a little show and tell there so that you can get visual aid. Today, when we go through our exercises, we're going to use this MC Miller orange box. There used to be one called the Nielsen, came in a little blue box, sometimes gray. It was a fantastic tool. It's no longer, you can find them out there, but it's no longer supported, so they don't sell them new anymore. That was the one I was born off of, but they all do the same thing and measure the same thing, which is resistance. That's what we're looking for. So moving on, introducing you again to that 4-pin Wenner method. This was invented by Dr. Frank Wenner. This particular method, we are going to utilize 4 probes or rods, and we're going to go hammer those things into the earth. Okay. So we're going to get 4 probes. We're going to hammer them into the earth, and then we're going to connect those probes to our soil resistance meter. Okay. Now, here's what I need you to concentrate on. Let me get my laser pointer for you. How we configure those probes matters. And what I mean by that, in this little illustration you have over here to the right of your screen, we've got our probes 5 foot apart, and we're doing that intentionally, okay? And so all 4 probes have 5 foot spacing, okay? I'm gonna talk in feet for a second. You can use any metric you want, but or any unit of measure, excuse me, you want, but today we're going to talk about feet. So we have them 5 feet apart. 5 feet apart means that we're going to measure resistance 5 feet deep. So whatever our pin spacing is in feet is going to be what the depth that we're going to be measuring is. So 5 foot spacing is going to take a look at the resistance at 5 foot deep. What happens when we go to 10 foot spacing between our pins? You guessed it. We're going to now measure the resistance at 10 foot deep. Same for 15 foot and so on and so forth. So you can imagine the deeper you want to look at, the further out your pin spacing needs to be. So if we went back to that measure tool and we said, look, I want to see what's going on 400 feet deep. That means that your pins have to be 400 feet in between each pin, or spacing in between each pin. So just to kind of give you an idea. All right. So the Wenner method is going to require us to put our 4 pins in. We're going to put them at a intentional spacing. Today, we're going to start at 5 foot. We're going to utilize a soil meter, and that soil meter is going to measure resistance. Now you'll notice that over here on the left of your screen, I've got a formula. Actually, I got 2 of them. So I've got a formula in feet and I've got a formula in centimeters. Okay. So we're going to be in feet today. So we're going to utilize that formula for feet to get us resistivity. Remember, we're measuring resistance. We're going to calculate resistivity. Resistance is in ohms. Resistivity is in ohm centimeters. And so the formula for that is, I'm going to give you a factor first, 191.5 times A times R. A is the spacing of our pins. R is the resistance that I just measured with my instrument or my meter, okay? If you were in centimeters and that's your preference, then you would use the second one, which is 2 times pi times A times R. A is still spacing, just this time it's in centimeters. R is the resistance you measured, okay? So moving on, we're gonna get out of this and we're gonna go to some of my homegrown drawings here, and you're gonna love it. It's a whiteboard here. So this is a professional drawing, okay? But no, I teach this way a lot. I'm kind of a whiteboard guy. I would much prefer to have one hanging on the wall, but since we're online here, this is what you get. So hopefully this will help you. Let's walk you through what I'm doing here. I've got my meter in the center of the screen right here. I selected the MC Miller soil resistance meter. I've got 4 pins put in the earth, and I'm showing you the distance in between pins of A, okay? That's going to be variable depending on the spacing I want to put, all right, or the spacing I want to have in between. And so we're going to list that as A today in feet, okay? You'll notice that each one of these pins I have in the ground, they're labeled C1, P1, P2, C2. So this particular meter has ports on it that have C1, C2, P1, P2 on it. So it's very specific with which pin you connect to that port or that terminal on that meter. Okay, it's very easy to follow. Highly recommend any instrument you use, read the instructions, take a look at the frequently asked questions and so on and so forth so that you fully understand how to utilize that meter. This meter is capable of more tests than I'm showing you today. A lot of people don't know that. It's a pretty powerful meter, actually. All of them are that I showed you earlier. But in this case, we want to make sure that we connect our C1 to the proper terminal on the meter, which will be labeled C1, so on and so forth. So we always have our P rods in the middle, okay, or inside the C's, okay. There's guys that have all kinds of sayings to remember that, because this is the kind of information that is very, very useful in the field, and also academically. If you're taking any kind of industry exam or course, this is going to come up. As a matter of fact, as you advance, so will this method, and you'll get into something called Barnes layering and some other things. So we're keeping it pretty simple today, but there's our illustration. We've got our pin set up. We're at a foot spacing, and now we're ready to measure, okay? And so what I have here is I have the 5-foot depth of the soil or the earth. I've got the 10-foot depth, which is the orange and the yellow. And then finally, I have 15 feet deep, which is the orange, the yellow, and the purple here. Okay, that was my color scheme for you. And so we're gonna set our pins up at 5-foot spacing first. That's gonna gain us measuring the depth of the resistance at the depth of 5 foot. Then once I get that off my meter, I'm gonna change my spacing of my pins to 10 foot deep. Now I'm gonna work my meter. And so 10 feet is the orange and the yellow section. And it's gonna give me a separate, different resistance value for 10 foot deep. And then I'm going to do the same thing. Once I'm done with that, let's change our pins to 15-foot spacing. Now I'm measuring 15 foot deep, and we're good to go. So I'm going to document, and I've got a nice little table down here for you. I'm going to document all of those measurements, those soil resistance measurements, and then we're going to calculate the resistivity together using that formula that I showed you before. So again, at 5 foot, we measured 32 ohms at that depth. That's 5 foot depth. And we're going to calculate resistivity. At 10 feet, we measured 14 ohms. We'll calculate that resistivity. And then at 15 feet, we measured 3 ohms, and we'll calculate that resistivity. So remember, the formula for feet is 191.5. That's a factor. And it helps you convert, times A is the spacing in feet, times R, that's the resistance we just got done measuring with our tool and pin setup, the 4-pin method, okay? So let's bring up this calculator. If you've watched my other videos, you know that I love this calculator. It's an emulator that you can purchase online. I think they let you use it for 90 days if you want to try it out. So again, we're going to calculate resistivity. We're going to do it for the first layer, which is 5 foot, because we had 5 foot spacing. And so we're going to go 191.5 times our spacing in feet. That's the A, that's at 5 foot, times the resistance we measured, which is 32 ohms. And we're going to hit enter. And that equates to 30,640 ohm centimeters. So 30,640 ohm centimeter. Now I labeled it there. Technically it's labeled at the top of this table, so I don't have to, but that is the unit of measure that we're in, which is very important for other calculations having to do with CP design and some other applications. So that's our ohm centimeter or resistivity at 5 foot deep. All right, got it. Let's look at 10 feet deep. Now remember, I'm looking at the orange layer and the yellow layer up there. And so we're going to do some calculations there. So we're going to go 191.5 times A. What's A this time? It's 10, because I'm 10 foot spacing and I'm looking at 10 foot depth. And then I'm going to times that or multiply that by the resistance I measured, which is 14. So 191.5 times 10 foot spacing times 14 ohms. And that's going to equal 26,810. So we'll go 26,810 ohm centimeter. All right, got it. I'm going to move down just a hair. And now we're going to take a look at 15 foot spacing or in other words, 15-foot depth. Same formula, 191.5 times 15-foot spacing times the resistance we measured, which in this case was 3 ohms. We're going to hit enter. It's significantly lower, and so it's going to be 8,617. So 8,617 ohm centimeter. Now that you did that, it's good to just stop and just take a look at your data, okay? And so at 5-foot depth, our resistivity, because we measured and calculated, was 30,000, roughly 30,000 ohm centimeter. Remember what I told you before, anything over 5,000 ohm centimeter was, in my opinion, kind of high. It can become very difficult to design galvanic cathodic protection systems in soil like that. Very difficult. It could equate to spending a whole lot more money on anodes and things like that. So that's pretty high. I don't know that I want to use that 5-foot depth for my galvanic anodes. Well, let's take a look at 10 feet. I could excavate down to 10. What is 10 feet looking like? Well, it goes down. It doesn't go down a whole lot though. It goes down to 26,000 ohm centimeter. So we went from 30,000 ohm centimeter to 26,000 ohm centimeter. So still pretty high. I don't know that I'm satisfied with that. Not sure I want to put galvanic anodes in a layer of soil like that. They may not work very well. Finally, I'm going to take a look at 15 because I probably could excavate that. I'm betting that my mechanical equipment can do that. And so once we calculate that, we get 8,600 ohm centimeter. That's getting closer to that 5,000 ohm centimeter mark that I was talking about earlier in the presentation. So 8,000 is looking pretty good. And this is a little more advanced. I don't want to confuse you, but because we're looking at the whole depth, 5 plus the 10 plus the 15 together, really down here at this layer, this purple layer, I bet it's lower than 8,600 ohm centimeter. Matter of fact, I know it is. In other words, it had to be to get that average down, okay? And so I'm feeling pretty good about that 15-foot range to put my anodes in. I'll probably design my CP system to go into that layer specifically, and I bet you it's going to yield better results than certainly at the 10-foot mark or that 5-foot mark. So there you go. What we've done is we've introduced you to soil resistance measurements. We've taught you how to calculate resistivity. You do have to understand whether you're going to utilize feet or centimeters because that formula changes. Now it gives you the same answer. The end result is going to be ohm centimeters, but it can really impact it if you get that wrong. So you need to know, am I in feet or am I in centimeters? Once you understand that, you can calculate it. Now you make sure you capture that data, document that data accurately. Now you can use that information, whether you're in an AC interference situation or a CP design situation or whatever it is. So there you go. There's the 4-pin Wenner method. We can introduce you to some more advanced topics concerning soil in another video. You'll hear something about Barnes layer, where you can actually take the information we just gathered and you can specifically do some more math. It's not bad. Specifically look at just that layer down there. For example, that 15-foot layer that we were looking at. So congratulations. You now have gotten yourself through soil resistivity for corrosion nerds. I'm Adam Johnston. I'm your corrosion coach. We'll see you next time.